This lecture is about the discriminative classifiers for text categorization. In this lecture, we're going to continue talking about how to do text categorization and cover discriminative approaches. This is a slide that you have seen from the discussion of naive Bayes classifier, where we have shown that although naive Bayes classifier tries to model the generation of text data from each categories, we can actually use Bayes rule to eventually rewrite the scoring function as you see on this slide. And this scoring function is basically a weighted combination of a lot of word features, where the feature values are word counts and the feature weights are the log of probability ratios of the word given by two distributions here. Now, this kind of scoring function can be actually a general scoring function, where we can in general represent text data as a feature vector. Of course, the features don't have to be all the words, and the features can be other signals that we want to use. And we mentioned that this is precisely similar to logistic regression. So in this lecture, we're going to introduce some discriminative classifiers. They try to model the conditional distribution of labels given the data directly, rather than using Bayes rule to compute that indirectly, as we have seen in naive Bayes. So the general idea of logistic regression is to model the dependency of a binary response variable y here on some predictors that are denoted as x. So here we have also changed the notation to x for feature values. You may recall in the previous slide we have used fi to represent the feature values, and here we use the notation of x vector, which is more common when we introduce such machine learning algorithms. So x is our input. It's a vector and with m features, and each feature has a value x sub I here, and our goal is to model the dependency of this binary response variable on all these features. So in our categorization problem, we have two categories, let's say theta 1 and theta 2, and we can use the y value to denote the two categories. When y is 1, it means the category of the document is the first class, theta 1. Now, the goal here is to model the conditional probability of y given x directly, as opposed to model the generation of x and y as in the case of naive Bayes. And another advantage of this kind of approaches is that it would allow many other features than words to be used in this vector. Since we're not modeling the generation of this vector, we can plug in any signals that we want. So this is potentially an advantage for doing text categorization. So more specifically, in logistical regression, the assumed functional form of y depending on x is the following. And this is very closely related to the log or log odds that I introduced in the naive Bayes, or log of probability ratio of the two categories that you have seen on the previous slide. And so that this is what I meant, right? So in the case of naive Bayes, we computed this by using Bayes rule, and eventually we have reached a formula that looks like this. But here we actually would assume explicitly that we would model our probability of y given x directly as a function of these features. So more specifically, we assume that log of the ratio of probability of y equals 1 and the probability of y equals 0 is a function of x. Right, so it's a function of x, and it's a linear combination of these feature values controlled by beta values. And since we know that the probability of y equals 0 is 1 minus probability of y equals 1, and this can be also written in this way, right? So this is a log odds ratio here. And so in logistical regression, we basically assume that the probability of y equals 1 given x is dependent on this linear combination of all these features. So it's just one of the many possible ways of assuming the dependency. But this particular form has been quite useful, and it also has some nice properties. So if we rewrite this equation to actually express the probability of y given x in terms of x by getting rid of the logarithm, and we get this functional form, and this is called a logistical function. It's a transformation of x into y, as you see on the right side here, right? So that the x's will be mapped into a range of values from 0 to 1.0. You can see, and that's precisely what we want, since we have a probability here, and the function form looks like this, right? So this is the basic idea of logistical regression, and it's a very useful classifier that can be used to do a lot of classification tasks, including text categorization. So as in all cases of a model, we would be interested in estimating the parameters. And in fact, in all the machine learning programs, once you set up the model or set up an objective function to model the classifier, then the next step is to compute the parameter values. In general, we're going to adjust these parameter values to optimize the performance of the classifier on the training data. So in our case, let's assume we have the training data here, xi and yi, and each pair is basically a feature vector of x and a known label for that x, y is either 1 or 0. So in our case, we are interested in maximize this conditional likelihood. The conditional likelihood here is basically to model y given the observed x. So it's not like modeling x, but rather we're going to model this. Okay. Note that this is a conditional probability of y given x, and this is also precisely what we want for classification. Now, so the likelihood function will be just a product over all the training cases. And in each case, this is to model the probability of observing this particular training case. So given a particular xi, how likely we're going to observe the corresponding yi. Of course, yi could be 1 or 0. And in fact, the function form here would vary depending on whether y sub I is 1 or 0. If it's 1, we'll be taking this form. And that's basically the logistical regression function. But what about if it's 0? Well, if it's 0, then we have to use a different form, and that's this one. Now, how do we get this one? Well, that's just a 1 minus the probability of y equals 1, right? And you can easily see this. Now, the key point here is that the function form here depends on the observed yi. If it's 1, it has a different form than when it's 0. And if you think about when we want to maximize this probability, we're basically going to want this probability to be as high as possible when the label is 1. That means the document is in topical 1. But if the document is not, we're going to maximize this value. And what's going to happen is actually to make this value as small as possible, because they sum to 1. When you maximize this one, it's equivalent to minimize this one. So you can see basically if we maximize the conditional likelihood, we're going to basically try to make the prediction on the training data as accurate as possible. So as in other cases, when compute the maximum likelihood estimator, basically that's to find a beta value, a set of beta values that would maximize this conditional likelihood. And this again then gives us a standard optimization problem. In this case, it can be also solved in many ways. Newton's method is a popular way to solve this problem. There are other methods as well. But in the end, we're going to get a set of beta values. Once we have the beta values, then we have a well-defined scoring function to help us classify a document. Right? So what's the function? Well, it's this one. See, if we have all the beta values already known, all we need is to compute the xi's for that document, and then plug in those values. That will give us estimated probability that the document is in category 1. Okay, so so much for logistical regression. Let's also introduce another discriminative classifier called k-nearest neighbors. Now, in general, I should say there are many such approaches, and thorough introduction to all of them is clearly beyond the scope of this course, and you should take a machine learning course or read more about machine learning to know about them. Here I just want to include a basic introduction to some of the most commonly used classifiers, since you might use them often for text categorization. So the second classifier is called k-nearest neighbors. In this approach, we're going to also estimate the conditional probability of label given data, but in a very different way. So the idea is to keep all the training examples, and then once we see a text object that we want to classify, we're going to find the k examples in the training set and that are most similar to this text object. Basically, this is to find the neighbors of this text object in the training data set. So once we found the neighborhood and found the objects that are close to the object we're interested in classifying, and let's say we have found the k nearest neighbors, and that's why this method is called k nearest neighbors. And then we're going to assign the category that's most common in these neighbors. Basically, we're going to allow these neighbors to vote for the category of the object that we're interested in classifying. Now, that means if most of them have a particular category, let's say category 1, then we're going to say this current object will have category 1. This approach can also be improved by considering the distance of a neighbor and the current object. Basically, we can assume a close neighbor will have more saying about the category of this object, so we can give such a neighbor more influence on the vote, and we can take a weighted sum of their votes based on the distances. But the general idea is to look at the neighborhood and then try to assess the category based on the categories of the neighbors. Intuitively, this makes a lot of sense. But mathematically, this can also be regarded as a way to directly estimate the conditional probability of label given data, that is P of y given x. Now I'm going to explain this intuition in a moment, but before we proceed, let me emphasize that we do need a similarity function here in order for this to work. Right? Note that in naive Bayes classifier, we did not need a similarity function. And in logistical regression, we did not talk about the similarity function either, but here we explicitly require a similarity function. Now, this similarity function actually is a good opportunity for us to inject any of our insights about the features. Basically, effective features are those that would make the objects that are in the same category look more similar, but distinguish objects in different categories. So the design of this similarity function is closely tied to the design of the features in logistical regression and other classifiers. So let's illustrate how KNN works. Well, suppose we have a lot of training instances here, and I've colored them differently and to show just different categories. Now suppose we have a new object in the center that we want to classify. So according to this approach, we're going to find the neighbors. Let's first think of a special case of finding just one neighbor, the closest neighbor. Now in this case, if let's assume the closest neighbor is the box filled with diamonds, and so Then we're going to say, well, since this is in this object is in category of diamonds, let's say, then we're going to say, well, we're going to assign the same category to our text object. But let's also look at another possibility of finding a larger neighborhood. Right, so let's think about the 4 neighbors. In this case, we're going to include a lot of other solid field boxes in red or pink. Right? So in this case, now we're going to notice that among the 4 neighbors, there are actually 3 neighbors in a different category. So if we take a vote, then we'll conclude the object is actually of a different category. So this both illustrates how k-nearest neighbor works, and also illustrates some potential problems of this classifier. Basically, the results might depend on the k, and indeed, k is an important parameter to optimize. Now, you can intuitively imagine if we have a lot of neighbors around this object, and then we'll be okay, because we have a lot of neighbors to help us decide the categories. But if we have only a few, then the decision may not be reliable. So on the one hand, we want to find more neighbors, right? And then we have more votes. But on the other hand, as we try to find more neighbors, we actually could risk on getting neighbors that are not really similar to this instance. They might be actually far away as you try to get more neighbors. So although you get more neighbors to vote, but those neighbors aren't necessarily so helpful because they are not very similar to the object. So the parameter still has to be set empirically. And typically, you can optimize such a parameter by using cross-validation. Basically, you're going to separate your training data into 2 parts, and then you're going to use one part to actually help you choose the parameter k here, or some other parameters in other classifiers. And then you're going to assume this number that works well on your training set would be actually the best for your future data. So as I mentioned, KNN can be actually regarded as an estimate of the conditional probability of y given x, and that's why we put this in the category of discriminative approaches. So the key assumption that we made in this approach is that the distribution of the label given the document, or probability of a category given document, for example, probability of theta I given document D, is locally smooth. And that just means we can assume that this probability is the same for all the documents in this region R here. And suppose we draw a neighborhood, and we're going to assume in this neighborhood, since the data instances are very similar, we're going to assume that the conditional distribution of the label given the data would be roughly the same. If D is not very different, then we're going to assume that the probability of theta given D would be also similar. And so that's a very key assumption, and that's actually an important assumption that would allow us to do a lot of machine learning. But in reality, whether this is true, of course, would depend on how we define similarity, because the neighborhood is largely determined by our similarity function. If our similarity function captures objects that do follow similar distributions, then this assumption is okay. But if our similarity function could not capture that, obviously this assumption would be a problem, and then the classifier would not be accurate. Okay, let's proceed with this assumption. Then what we are saying is that in order to estimate the probability of a category given a document, we can try to estimate the probability of the category given that entire region. Now this has the benefit, of course, of bringing additional data points to help us estimate this probability. Right? And so this is precisely the idea of KNN. Basically now we can use the known categories of all the documents in this region to estimate this probability. And I have even given a formula here where you can see we just count the topics in this region and then normalize that by the total number of documents in the region. So the numerator that you see here, C of theta I and R, is the count of the documents in region R with category theta I. Since these are training documents, we know they are categories. We can simply count how many times we have seen sports here. how many times we have seen science, etc. And then the denominator is just the total number of documents, the training documents in this region. So this gives us a rough estimate of which category is most popular in this neighborhood, and we're going to assign the popular category to our data object since it falls into this region.